Here we go, lesson 33. This is applying the counting principle. While it sounds simple enough, there is a little bit extra to it, and it makes for some interesting math problems when we get down the line. At first it starts out a little boring, but it gets interesting as we go. So when they talk about an experiment, it's literally just that, an experiment. Okay, it's any process that results in one or more outcomes. So an outcome is what happens due to something that we try. So flipping a coin, if it lands heads, that's an outcome. The experiment is trying to figure out whether it's going to land heads or tails. Each trial is us flipping that coin. So if it says flip the coin 50 times, there's going to be, the experiment is flipping the coin 50 times. The outcome is each head or tail we get, and then every trial is each time we flip the coin. Okay? So on example 1, we're just going to talk about that one using a tree diagram. It's talking about ordering a sandwich. So there's 3 different types of meat. So basically the thing that goes in between the bread, right? So there's 3 different things that you can put in between. There's turkey, ham, and chicken. So turkey, ham, and chicken are the types of sandwich that you can get. But from there, we can add different types of bread, and we have 2 different options. So I'm just going to put chicken instead of chicken salad. So for turkey, we have rye or wheat on every single one of these. So we get rye or wheat on every single one of them. So now my options for sandwiches, I started out with just 3 types of meat and 2 types of bread, right? So I have 1, 2, 3, 4, 5, 6. I have 6 options for this. Now, without having to draw all of this, and this is the beauty of the counting principle, without having to draw all of this, I can say 3 times 2 makes 6 outcomes. All I have to do is multiply it. So it really just eliminates you having to draw these huge sample spaces. This is a small one. What if it said you have the options of turkey, ham, chicken on rye or wheat bread, and whether you want American cheese or whatever kind of cheese. It gave you 3 different types of cheeses. Now you have the options of 18 different sandwiches. But we don't want to create a sample space for 18 different sandwiches. That's crazy because I got 1, 2, 3 coming off of each one of these because I have 3 different types of cheeses to come from. 3 different types. Have you guys ever seen that sign at Sonic that says we have 250-something thousand drink combinations to choose from? I counted them. They're not lying. I used the counting principle, and you take how many different types of drinks they have, how many different flavors, and how many different real fruits or whatever you want, and you just multiply them all together. So it took me like a minute. What about slushes? Yeah, you add all those in. But anyways, it's really interesting. It's really interesting. So where they come up with that number isn't somebody sat there and went, all right, we're going to figure this out. There's nobody that did that. Okay? They just said, okay, there's this many options, there's this many options, there's this many options. Let's find out how many there are total. And they just multiply. Okay. Y'all guys know that this is called a sample space. Okay? So I'm not going to go over that definition anymore. Where we start talking about the addition sample space, I'm going to read the addition counting principle. I'm going to read their definition, then kind of shorten it down. Suppose a trial can result in any of n outcomes. They use n as a general term for number of outcomes from one category, and any of n sub 2, which is just another set of outcomes, from another category, and so on. There are k different categories, so blah blah blah, however many categories of outcomes, and the total number of outcomes that can result is, and then they just add them all together. So the adding principle says if there are so many outcomes, we can simply add them all together. We're going to do an example that'll better explain that. Okay, example 2. It says, using the addition counting principle, find the number of outcomes for each event. So if we're talking about drawing an ace or a face card from a deck at random, a standard deck has how many aces? It has 4 aces. How many face cards does it have? It has 3 different face cards, and there's 4 in each of those, right? There's 4 queens, there's 4 kings, and there's 4 jacks, right? So how many total? 12. So there are 12 and there are 4. If you count them together, you literally just add them. So there are 16 in total, right? So drawing an ace, a face card, from a random standard deck, you have 16 available outcomes. So it's that easy, 16 outcomes. You just simply add them together. Any questions there? I didn't figure there would be. On B, it says choosing a prime number or multiple of 6 or a multiple of 10 by choosing a number at random from a whole numbers 1 through 20. So I could literally list the numbers 1 through 20 if we wanted to do that, and then eliminate them, which is probably the way Taylor's going to do it because she likes to do it the long way. Okay. So let's think about what these numbers are. So for the sake of Taylor, we're going to go ahead and list these out. Being sure makes you smart, Taylor. All right. So I got all of the numbers listed 1 through 20 on my paper. And as I find them resulting from what they tell me, I'm just going to put a mark through them. So any prime number, so 1, 2, 3, all prime, 5, 7, 11, 13.
Prime was neither, or 1 was not prime or 2. That's weird. That's 1.
There's a matter of debate. I will go with you guys on that one, I guess. Okay, 1 is neither prime nor composite. So I'll leave it. All right, we got 19, 17. Anything else? Okay, all the rest of them are even or got something that go into them, right? So now we need to go through and find all multiples of 6. So multiples of 6 are 6, 12, 18. Good there. Or a multiple of 10. So 10 and 20 are out. So now I can either add up all the slashes that I made, or I can look at the ones that are left and subtract that from 20. Whatever you want to do, I don't care. Just add them all together. There should be 13. Is that right? So 13 total outcomes. Now somebody's going to say there's got to be a shorter way. Yes, there is a shorter way. You could just count all the numbers 1 through 20 that are prime, and then write those down. I think there were 8 if I look at it again. Anyways, and then you can count the multiples of 3, add those in, and then the multiples of 20 or 10, which were 2, and then add them all together. Either way, we're going to get 13, so I don't care how you do it, just do it. Okay? Now, here's the one that I find more interesting, and the one that we used in our example. The fundamental counting principle allows us to do this. Okay, that's what Sonic used, is the fundamental counting principle that allows them to do what they do. They just multiplied things together. So the long definition basically just says if I have something that I want to find total outcomes for in combination, I just multiply them together. So example 3, and this is how you'll see a bunch of these problems presented, so get used to it. A student is choosing a 3-letter password for an email. So I have 1, 2, 3 letters, right? How many passwords are possible if the letters may be repeated? How many letters are there in an alphabet? 26. So I have 26 options for the first letter. I have 26 options for the second letter. And I have 26 options for the third letter. In order to find out how much that is, I just multiply it. There are 17,576 total possible passwords that she could choose from.
Okay, now if this is like the same problem but they were saying like it couldn't be repeated, would it be 26,
25, 24. Okay. Yes, indeed. If they could not be repeated, we would go down every single time. Now that's what makes those 4-digit passwords interesting, is because somebody out there has your same password, right? And if you think about keys for a house, okay, those keys somewhere in this world, somebody has the keys to your house. Obviously, they don't know about it, right? That's why car manufacturers switched their keys to have a code in them, because some of their keys were very similar. And if you put a code in them that's cryptic, that's 10 or 20 digits long, it will never, ever, ever, ever be repeated.
Like in older days before, like my mom locked her keys in her car and her teacher's trunk card key unlocked her pickup.
Right. I used to do that with a lot of Chevys. Every single Chevy short wide used the same key for a long time. Yeah, it was scary. So that's why car manufacturers started doing that. It was really hard to make new keys, right? All right, so let's do another example. Example B here. Not necessarily. Just because we're not going to have a lot of time. Okay, on B it says how many passwords would be possible if they were not repeated. So we would have 26, 25 times 24. And then our options would go down per letter because they can never be a repeat. And then we just find out that we have only 15,600 possible options for passwords. There you go. All right, now let's talk about the difference between two things. We have two events that are independent if the probability of one does not affect the other. So see how this one did not affect the rest of them? So part A did not affect. On part B, however, it did affect. So if we're looking at dependent, it says the probability of one event affects the probability of the second event. So here I have 26 letters to choose from, but here I have 25. So the probability of me guessing this one on my first time is 1 in 26. My probability of me guessing this one is 1 in 25. Okay, so the probability goes down. If it's independent, it doesn't affect it. If it's dependent, it does affect it. Okay, they'll ask you to identify that later, so that's why I'm giving you those definitions. Example 4. I'm running out of room here. Example 4 says letters A through E are written on 5 index cards. 1, 2, 3, 4, 5. Keeping in mind A, B, C, D, E, only 5 letters, right? All right. So from here, it says determine whether the events in each case are independent or dependent. And a card is chosen at random, and then another card is chosen at random. Did it say it was replaced? No. So in the question, it specifically states on whether or not the card will be replaced or not. And that will depend on whether it's independent or dependent. So question A. It says choose A and then choose B if the first card is replaced before the second card is chosen. So it is replaced. If it's replaced, it's what? Independent or dependent? It's independent because the probability doesn't change. I still have a 1 in 5 chance, right? 1 in 5 chance here. If I replace the card, I still have a 1 in 5 chance. So I'm only choosing 2 cards, right? So if I'm only choosing 2 cards, it's going to be an independent solution. And I will have 25 possible combinations. Okay?
So you have a 1 in 5 chance.
I have a 1 in 5 chance here and then a 1 in 5 chance here. So in combination of me choosing 2 particular cards in a row, it's 1 in 25 because I multiply them together. Right? This question is specifically just asking if it's independent or dependent. So it's independent on this one. On part B, it says that the cards are again chosen, A, then B. And if the first card is not replaced, then the 2 cards chosen will go 1 in 5 and then 1 in 4. So the probability of choosing them together would be 1 in 20. And because of the probability changes, it changes us to a dependent event. Currently I'm just abbreviating today. Okay, any questions there on independent and dependent? I figure we would. That's really all that you technically need to get this lesson done. Do y'all want to go over example 5?